Hi, everybody, and welcome to Neuroscientists Talk Shop, UTSA's Neuroscience Research Podcast. Today is November 7th, 2024, and we're talking with Carlos Bassetto, who is assistant professor in the Department of Physics and Astronomy here at UTSA. Carlos is a biophysicist who studies the inner workings of ion channels. These are the membrane molecules that are responsible for all the electrical signals that run our nervous system, our glands, and our muscles, and our thinking and our talking. And he is a new addition in our physics and astronomy faculty. We're really happy to have him at UTSA, and we're really happy to have him here today.
Thank you.
Carlos.
Hi, how's it going?
Great.
Glad
So,
to be here.
also with us is Fidel Santamaria, also a biophysicist, but he's been here a little longer, and is a veteran podcast participant, I think, right from the very beginning.
I was a guinea pig, Charlie.
Yeah.
Mm-hmm.
So, hi, Fidel.
Hi, Charlie.
And I'm Charlie Wilson. So, Carlos, our current understanding of ion channels is one of the great accomplishments of the last century of neuroscience, and it's the foundation on which everything is built.
Exactly.
And the story of the discovery of ion channels and how they work is this incredible saga of people that didn't have any direct way to measure the molecule, but were measuring them really indirectly. And they were able to just surmise that there must be a piece of the molecule that moves up and down when this happens, and another one that opens a little door to let ions through, and another one that closes the door. And they made it all of that quantitative so that their models could predict ion channels really accurately before they knew really much of anything about the actual structure. Now, though, we're lucky and modern, we have the ability to actually see the molecular structure. And so there's an opportunity to go back to all those discoveries and fit them into a molecular framework of the protein structure.
Exactly.
So could you start us by giving a little bit of an overview about what the electrical measurements are that allowed us to know what the parts of the ion channels are? And I know there are a lot of different kind of ion channels. You could pick your favorite one as an example if you want to.
Sure.
And then give us some notion about where we're going now that we can see the actual molecule.
Sure, absolutely. Yeah, it's very interesting. When you think about it, how people, like since from Hodgkin Huxley, when they did all that particular description of the action potentials and the sodium potassium currents, and then they kind of predict and propose that should have some particles, right, that move. And then later on, Pancho and Clay Armstrong, Pancho Vesanilla, they actually measured those particles. And then later on, you have the measurements of the single channels people were able to see the open and close of these particles.
Just the fact they called them particles tells you they didn't know what they were.
Exactly. And then it's interesting that only in the 80s, when they start to clone all of the channels, they start to see they have like charged residues, the amino acids, then they were positive, and then they were in the membrane, and then they said, probably here is where it's moving, right? And then, of course, with the new techniques from the time, when you start using mutations, and then when you do a mutation, if this is important, I should change, and then that's how it was changing. So you start neutralize those particles, and there was a lot of knowledge. Right now we know that we have the gating currents, that the gating particles, what is the residues that move, and how those residues move, and they are all connected to these linkers that later on is connected to the pore, which now we know with all the revolution that was started with X-ray with Rod McKinnon. And then nowadays we have the cryo-EM that people now can really see those channels. But in the past, I wonder how they came up with all of these nice models.
Well, I think some reviews, it was Hodgkin Huxley review, in which you can read, I wish I had the reference, like, look, I mean, is this a breakdown of a capacitor? Like, is it just like zapping? And then there's a hole in the membrane. And then they go and say, look, it's it's just too fast. Like the action potential is just too fast.
Mm-hmm.
There's a reversal thing that people were seeing.
And ion selectivity was a key thing.
Yeah, but they had like
That was the
paragraphs of like arguing, is this just like a hole making, right?
Yeah.
And the timing and then the experiments of ion selectivity said, then that's probably not that. And I think it's in their novel lecture that they say, well, maybe they also say, well, this is a model. We don't even know if this is true. But they were imagining that these things were coming and still prying opening. Like the particles will come and kind of like push and open and close and leave, right?
Yeah.
So it was not like embedded in the membrane. And then it's later when we start understanding that proteins are exposed on the membrane and start building this idea that they were almost monolithic, right? It's just a thing that it either opens or closes, right? Just as if at the microscopic level in a continuous way. And as you're saying, it's until the 80s that we realized that no, they're like random things opening and closing, and they have different states.
Yeah.
And then when we start understanding how proteins change conformational states, then we add one or two, the ideas, right? But still thinking about as a monolith. Now with like a ball and chain or a knee rotating and opening the channel. And now that we have access to we can put them in motion in a supercomputer, it's all shaking. It's fascinating to see these kind of 20 nanosecond movies, right, in which everything is moving, right? And it's bombarded by the temperature, by the thermodynamics of the lipids colliding, right? Water colliding, and the entire thing is shaking. So it's interesting to now see then how energy moves there and all that stuff.
Exactly. Yeah, it's a good point that now we can see, predict, and try to make sense of the data that we have now, and we have a lot of data.
So, what are the typical data consist of? Like you mentioned, just measurements of currents through channels that open and close, even single channels. That's possible to do.
Yeah.
And then gating currents you mentioned were currents that are kind of illusory.
Oh, yeah.
They are currents that happen, like capacitative currents that happen when these voltage-sensitive particles jump around in the membrane. And so those were the original measurements that people had. But now we have, what are the right molecular, we have the protein sequence, we have the amino acid sequence, and modern ways to try to guess what that configuration is.
I would say that gating, we still get a very nice measurements with that. As you just said, now we know exactly the proteins, we can do mutations there. And just to give an example, how much charge are those residues moving? One single channel, let's say shaker, right, has, like, let's say in the whole channel, like 13 elementary charges of the electrons. So this is very tiny. But when you put all of them together in a huge preparation, then we can start to see all of those because they are essentially like capacitive currents. But now we can not only see the gating, but we can use fluorescence. So we can put like optical probes and we can attach to these ion channels, and then as the voltage change and these particles move, the fluorophore would experience a different environment. So that tells us also about which part of those proteins.
This is one channel at a time. So there's one fluorophore. No, this is looking at
we are seeing one fluorophore from one channel. We have imagine you have those voltage sensors. Usually for this potassium channel that I'm just referring, there are 4 voltage sensors, and then those voltage sensors you can attach one fluorophore. In our case, one can use cysteine, for example, and then you do modification with MTS. And that chemical reaction will happen. Then you attach covalently like a fluorophore. And then when we change the voltage there, then we see that one. But then what we measure people, I think there are some people trying to do like single molecule, but this is super hard, which be equivalent for the single channel idea that you see only one molecule moving at a time of those.
Per voltage sensor.
Per voltage sensor. But what we truly observe is just like the average of all of them moving in the membrane. But there are other techniques also that are based on how the photons like interact between itself. For example, the LRAD or FRAT RNAs that people have done experiments, so you can sort of there's a kind of 3D point and see how they work if you put like a sensor here with fluorophore here, so they will interact, and that will generate like a difference in the signal. There's a way that people can measure it, make sense of those data. So we can go very now narrow in the molecular base of how they move, and also which this is what we experimentally using electrophysiology that we can achieve, like even seeing the ionic currents. For example, one can try put one fluorophore in one of these channels, and instead of measuring gating, measuring ionic currents. But more recently with cryo-EM, there has been like some reports of researchers trying to. There are mutations that you can have a channel in a let's say one state, let's say in the resting state, which is the closed state of this.
So this is a mutation that forces everybody
Exactly.
into the closed state.
Exactly. And then you try to get the image, the cryo-EM.
So tell me about that.
Oh,
How do you do that? What kind of image do you get?
Oh, that's you have to use a lot of. So first you need a nice. I don't do that myself, but we hear here and there how people have done that, right? And essentially, you have to have a lot of protein, and then you use you isolate these proteins, and then you suddenly freeze. So everything stays in the condition that was before, and then you use electrons. And then this electron goes here, and then you have a camera. And then after that, you have like a diffraction pattern. It depends on which kind of interaction that the electron is going to be, the beam. But then you build that using like computational methods. We don't see it, but we have to later on kind of use a processing to. It's kind of if you use like it's the same in the X-ray when you have like the Brillo one that you then reproduce back what would be. But then it's super interesting because
that gives you a two-dimensional projection.
Give like a three-dimensional projection, and then if you combine 2D. But
so you have to look at ones that are in all different. But if you just laid them out sparsely, some of them will be in every. Exactly. But you have to. How do you figure out? Like here, you have a whole bunch of pictures of ion channels at all different orientations.
Yeah, that's
how do you sort it? How do you figure out what orientation each one is at?
Most of the cases we need to have like sort of a model to build you have to this should be the outside, this should be the inside, because there are parts of the channel that we recognize. And then I think as I mentioned, not expert in that particular kind of measurement, but then you lay it out and then you train like a program to build up all of them together and stack. And then with that, you generate it spits out what would be this model. So essentially, it's a model still, but it's a very nice because that can provide a lot of information that later then you can use that. For example, if you have a mutation now, this what should be or could be the closed state, and then you have one that would be the open state, and then you can later do in a computer. How they would go from the closed to the open state in a sort of a morph, which is now you kind of combine everything, and then I see ultimately how.
Yeah, just to complement your point, I think there's an iterative process that then you come up with a result, like it could be machine learning, whatever, and then you use you have the sequence, and then you have an idea of how that would, or if you have it crystallized, and then compare what you get with the stuff that you have, and then is it similar or not, or is it giving you a blob that doesn't have anything to do with the
or
the sequence?
you can to validate, right? We need to, because I mean, even though the structure is interesting, but it's based on a model. And then, as you said, we need to validate, and one can validate using electrophysiology. So you can say, okay, if this part here is really in touch or in connection with this part of the protein, I can engineering like a bridge, for example, like a cysteine bridge. And if they were connected, I should be able to predict that when I do a modification of those cysteines, they should connect it, and that would change. So we still need to validate it after with it. I think when you combine these two measurements, then you are in very good shape, because then you can really learn a lot.
So we normally think of channels as having discrete states. So you get a snapshot of the closed state, a snapshot of some open state. There might be more than one closed state and more than one open state, right?
Probably.
And sometimes you've just got them all in some state.
Exactly.
And then maybe there's an inactivated state too, and you can get them stuck there. So the transitions between states, because even though conceptually we like to think of them, any one channel is in one of these discrete states, but they really have to transition at some point from one to the other.
Exactly.
So I guess you just sort of fill that in. I mean, it's like you've got frames in a movie and you fill in the frames that lie in between these states.
Exactly. You make like a movie.
Well, that's what I meant by this kind of almost, we have begun transitioning from a monolithic to a semi-monolithic, and it's kind of this Lego thing that just jumps.
Yeah.
But it cannot, right? It's something, and it's more flexible than what we have imagined.
Yeah, as you said, there are many states, and we try to, let's say, in a way that we try to explain the transitions or the states in the minimal number of states. Otherwise, if you do like a modeling, it can get too big that you can see anything, because you can modulate that in the way you want. But if you reduce a lot the number of models, and if that reduce very small can predict the currents and the outcomes, then is a state. It is a model that say, it's a minimum model, we can use that. But in reality, I believe that we have a lot of states, and it's hard to pinpoint all of them, because we can say, one voltage sensor moving, it might be only one state and the other. And
of course, the states that we usually put into the models were made before people had molecular structure.
Yes.
So the models were made based on experiments where you held the cell at one voltage and then you jump to some other voltage and then you jump back really fast, and these really clever experiments to try to pull the channel into one state and then move it from there into another. And they came up with these amazing diagrams with the transition probabilities and everything in them. And so that must be a huge benefit to people now analyzing the molecular structure, because those states, I guess they're kind of, they're not absolutely positively right, but they're pretty close.
They're pretty close, exactly. You're right. And in the past, and I think now we can revisit a lot of the things that were done in the past, and because learning, of course, and see the models now with the new structural data, we can actually see if those models were, how accurate they were at the time. But I think it's amazing how people have worked so hard and got a very nice and close, accurate model from what we see nowadays. And we can describe most of the things, at least the functioning of an ion channel, even like how an action potential would work with those models, which I think is amazing. That in a very nice.
So one of the coolest things about it, to me, is this sort of modularity of it. So the molecule's got these different pieces that have identifiable jobs. So you could point at one piece of the molecule and say, this is the pore, and this is the part that opens and closes, and this is the part that pulls it here to make it open or close, and this is the part that moves when the voltage changes. And all those parts are really there. And originally those were, let's just imagine that the molecule is built like that.
Exactly.
But there have been some revisions of these ideas as you've actually seen the structure. Do you have a favorite thing that turned out to be wrong?
it's hard to say that was wrong, but it was one interesting is that the inactivation of the sodium channel is a very
Right.
interesting one. That before was proposed the ball and chain, so there was a piece that would go in the pore and would plug in. Conceptually, it was a nice, but nowadays revisiting it, actually it seems that there are some residues in the pore, in the S6, that there's a transitioning happening that goes to those residues, and those are the ones that close.
So it really just turns out to be another gate. Not that different from
Yeah,
the
but
act.
I mean,
that's a very
Is that not true?
it's hard to say is another gate. Could be another gate. We can call inactivated.
See, there was an old controversy a long time ago about whether it was really a voltage-driven gate or whether it was an open channel block.
Yeah.
So let's just be clear on what's the difference, because it's a difference that may not make a difference too much, but it matters for the structure.
Yeah.
So another gate would have its own voltage sensor. That voltage sensor would move and close that gate, and the delay between opening and inactivation would be because of some delay in the molecule. Yeah. Whereas in the other model, and I know there are ion channels that work this other way too, where when the channel opens, it allows something to come in and block the channel, and so it's really just the opening that causes the block.
Yeah.
So I mean, those are kind of extreme positions to take, and there could be some compromise solution.
Yeah, absolutely. And I think, like as you said before, it needs to open completely, and then something goes in, right? That is a voltage dependent because you need the voltage sensor to trigger that. Now, the change in paradigm is that you open this, and there is a transition that happens, and that transition is not essentially something that goes in the pore. It's something that just closes it, but it doesn't go in. It's just like laterally.
But it doesn't have its own voltage sensor. It's just a thing that happens after the voltage.
You need the voltage sensor to initiate this process. Okay.
But it's the same voltage sensor that opens the channel, or is it a different one? It is the same.
It's one of those.
But
they are connected.
And it depends on time.
It depends on time.
I mean, that's the fascinating part for me. So the longer you keep it depolarized, the longer it will take to recover from the block state.
Yeah.
That's the problem, right? So if you clamp it at minus 20 millivolts for 10 milliseconds, 100 milliseconds, or a second, then the recovery time from that closed state is different. So that means that there's something else, right? And you can have extending the monolithic state model to like an infinite number of hidden markup states.
Yeah.
Right? More and more hidden markup states. And then your system goes into those closed states and it gets lost. And then it takes a while to come back to the opening of the cave, right? And then it opens again. But you can think about going back to this thing that now every part is moving all the time and integrating the idea of allosteric states. That every state could be an allosteric state.
What does that mean?
Right? That the activation of one state is going to influence the transition states of other states. Okay? And I mean, this comes from like small molecules affecting, for example, mGluRs, but you can think about that in all proteins, right? And some people have been saying, look, this is what is happening is like one of these states, whatever it is, it's not completely clear, is then changing or is in like the more the channel is depolarized, that is affecting the transition state of the reopening. Right? They're not independent. Right? It's not a Markov chain.
So do we have structural data to address this question?
Ooh.
It's more classical electrophysics.
I know it.
Yeah.
Computations.
So I don't know if there's all atom simulations that could tell us.
That would require a lot of computational.
That would be a long.
Yeah, it's a long. That's I think the bottleneck of it right now. But
But the electrophysiology
No,
shows
you can.
this
You
kind
can actually. You see, for example, the recovery from inactivation. You see like the charge mobilized, right? You see less charge, as if you have lose some of those charges, but you're not losing it. It's just like slowly returning, and you need that return. Once that is completely moved back to the, let's say, the closed state, then you can reopen and see the true currents. And of course, this depends on time and voltage. So if you apply like a huge voltage, that process is going to be faster. And the molecular basis, still we don't know we have some ideas, but we don't know exactly what makes it to be stuck, and then you need voltage to remove it. If there is some other interaction that it needs to kind of break down, and then you move it back.
But do you think this is one molecular mechanism that just gets pushed too far, or that there could be another one that gets that happens with these like really prolonged depolarizations? Or I mean, I know Fidel likes to think of single mechanisms that work on lots of time scales, and it could be like that.
It could,
but traditionally, ion channel physicists have liked to think about things with single time scales that
it's more because then it could be many states, but then again, if you start having more and more individual states, then it becomes harder to also, because we need to fit those data to see. So essentially, when we fit our, let's say, our gating or ionic currents, let's say the minimum number of exponential that we have there essentially reflects of the minimum number of states. So if I have like 2, I need 3 states.
I think if what you're doing is trying to figure out what are the rates for all the transitions, the more transitions there are, the more rates you need, and the more experiments it takes.
Exactly. And then some of them are hidden. Maybe you cannot even fit them. So that's why it's hard to say whether or not we have more states specifically on that. But I think, I mean,
my point there is like you can model these things with 2 states that are outside equilibrium. That the closed states influences the transition rate of the open state. The longer the closed state is, you are in one state.
I see.
So it's outside equilibrium.
This has been sort of anathema for ion channel modelers.
I know.
Because
now it's out there.
Of course, that doesn't speak to what's true. That just speaks to what was practiced. Because solving these Markov models is hard, and if you introduce this kind of thing to them, they become
more harder.
And there's a lot to gain from Markov models. I mean,
So one of the things that sort of struck me is I checked today, and the textbook that we use to teach neurobiology class, I'm not going to mention which one it is because it's a great textbook otherwise, but it has this ball and chain model for the inactivation of the sodium channel. And I was reading a paper of yours, and you start by saying, well, long time ago, we believed in this ball and chain thing. That was replaced by this kind of flap type thing. And now I'm going to show you that flap is not actually the answer. And I thought, wait, we're still teaching a long time ago model? I guess it's because it's so appealing.
Yeah, it's so easy to understand and so appealing, exactly, that it's easier to see, something is going to go there and walk there, right? And now, as we delve more in towards the structure, it becomes more complicated because now we have different parts of it that was involved in the process, and which then you become something that was so simple, something just go here and look. Now, then you have this transition goes to that transition, this, and I think that's the beauty of the what was proposed before. But of course, we need now that we can see in a more accurate state. I think that's also nice.
But I guess at one point that's going to be like the Bohr model, right? It is not how the atoms work, but it's
how we want to think about it.
We wish it were.
Of course, that there will be a point that we need to do more introduce a little bit more complexity, but it depends from the purpose of what we want to see. Sometimes a simple model is as good as a complex one.
Yeah. What remains true is sort of the basic assumption that the thing is like a little mechanical machine.
Yeah,
that you could make it out of wood and springs and make a model of it that would work. And that's the first time I saw something like that, I thought that's not how chemistry is. Chemistry isn't like that, but these ion channels really are like that. And it turns out there's lots of other molecules that are like that.
ATPase.
Yeah. All of these molecular motors. And transporters.
Right.
It's remarkable that
it is.
When we can zoom in on them enough, they become more familiar, not less. They start to look like the kind of things that we would build ourselves.
Exactly. I just think this is a very nice analogy, such as that for those channels we call electromechanical coupling model. So we need a electrical part that senses the voltage, and then is connected to what we call mechanical part. So you need to pull, something is pulling and pushing the pore, and exactly, you can think of this like you can sort of, I wish I could do like a 3D printer of this and play with it. Maybe we can learn more, right? That's why the structure is nice. And I think that's the beauty of it. I think that's how we can, and then you can, one can even try, okay, how about if I take this piece combined with the other piece and to the other piece and see if that works, sort of using different parts of it and play like Lego, right? And you can take like from other channels or other proteins and see if they would work in the same way, or you can flip them around. I think is something it's nice, but I mean, sometimes
you're doing that with mutations, right?
Exactly.
I mean, that is
mutation.
Sure, you're changing some residue that is polar, non-polar.
Exactly.
And then you're changing a module. I mean, it's changing a lot more. It's changing the tertiary structure of the protein, probably, or probably more.
No, and I think that a nice way to think about mutations is that sometimes we need to get more information about it. If you modify, and if that modification is affecting one of the process that we think that's how it's working, then you can learn about that process. So there is a way that you can specify, like, for example, to measure gating current is a big deal because you need a lot of channels and you need to block those channels. But now, like, there are mutations that they block the conduction. So now you can only see the gating particles moving. And then with this, you can learn a lot of all the movements of the gating particles itself, which is sometimes if you don't have those, it'll be way more harder to achieve those measurements, which can get, I mean, now with the mutations, you can go a little bit easier and understand better, but if you don't have, then it would be hard. Or now, let's say if we want to imagine that the voltage sensor requires 2 transitions. Now, if we stabilize one of those transitions using mutations, you can see the 2 transitions individually. Sometimes it's hard to see those because they're so fast. So I think mutations is a nice way also to use them to study because we can learn a lot.
So there are a lot of different ion channels. Yeah. And there are some common design themes that go across the ion channels, but a lot of them are really different from each other. Is that not true?
I would say that the common theme is that they conduct ions.
That's the only common thing?
No.
But all of them came up from potassium channel.
There are, so some of them, they conduct different ions. Some of them conduct non-selective, so they conduct everything. Some of them are voltage-dependent.
Like molecular
themes. I would say the pore is something that needs to be there, or something that resembles a pore.
But they don't always work the same way. The gates don't work the same way. The voltage sensors don't work the same way.
Voltage sensors between the voltage gated, they are, I mean, there's a lot of resemblance. But imagine, like, even the potassium channels. So the architecture of them, sometimes they're not the same. So by saying that, for example, we have the voltage sensor and then we have the pore. Some of them is called swap domain. meaning that the voltage sensor now interacts with the pore domain, with the neighboring subunit. And some of them are non-swapped, meaning that the voltage sensor interacts with the pore from the same subunit. And in the same family, those is the way that they open and close, they're very different in a way, because then you need the linker that connects the voltage sensor to the pore. They're different. They're shorter in the non-swap domain. They have other connections to the pore. So they have a lot of similarities, but also they're not quite the same. But the pore, I would say, would be something that's common thing. But then, of course, some of them are temperature dependent. Some of them are tension dependent. So there are many ways that we can trigger, or even ligand.
I'm trying to get an idea about the size of the task ahead of us. Like if we're going to say we understand ion channels, like let's say we understand ion channels well enough so that somebody says, oh, this disease is caused by a mutation in this ion channel right here. That we would know about that ion channel well enough that we could kind of zero in on what the defect is,
I think
do something about
there
it.
are things that can be done in that regard. There are also, what happens is that sometimes patients, they have mutations and then they isolate it. They see the genes and sometimes they found some mutations in the ion channels. And then what people have done is that they take those mutations and they isolate in a system so we understand the biophysics of that. So this is something, but I don't think we understand completely. I think there's a lot more to know about them. But looking, I think there is kind of controversial to try to use CRISPR. I think, if I remember, is the what's the name of CFTR? Is the one of the disease that happens in the lung. It's a mutation in one of these channels, and then it's hard for the person to breathe. And so maybe with this new genetics, one could try to. Yeah. But I think we are far from this right now. We don't. I think, but it would be a way of actually treating that. I remember there was a mutation, but I forgot the specifics. Yeah. But I think it's fibrosis.
Cystic fibrosis.
Cystic fibrosis. I think that's the one that happens.
Like the Cardens.
Yeah, it's one of these mutants. And so I think that would be one way of kind of going, or even modulators in a disease. So some modulators, you need to block one of those channels. And sometimes you block them by accident, and that's not good for us.
Going back to Charles, but it seems that we're closer, right, with the AlphaFold and predicting for mutations. You could come up with any mutation and then come up with the conformational change. And then a little bit of, you can run a prediction of how the conductance is going to change.
I think that would be.
I mean, it seems almost plausible that we're close to that for any mutation.
I don't know yet if AlphaFold is there to predict mutations. Mm-hmm. It seems that for point mutations, it's not very well. I don't know if this new model.
There's a new model.
Yeah, I don't know if that new model they fixed that, but one can see. I mean, the AlphaFold is amazing that you can see the protein, right? What's built from.
Yeah, you can reconstruct the three-dimensional structure of
which
the protein
is great.
From a sequence.
And I think that if now, when we reach to the point that you just mentioned, that you can go mutation and see what happens, that would be like the dream. But I still have the feeling that we still need to do the experiment.
Yeah, no.
You validate.
But at least have a pipeline of probing multiple mutations. Say this is going to be the most important, and then at least you can align your experiments in a way that you're going to maximize the information.
Would be nice if
it wouldn't solve it. It just
something that would be nice, but I don't know if we have enough data for that, or that would be a huge work. Try to do like all the point mutations in one of those channels, and then feedback this in a system to see if we, in the AlphaFold system, let's say, if we can then later on predict how would be the voltage sensor given one, the voltage dependence given one mutation, or if we decrease the conductance. But that would be like amazing. And I think what really is nice about this, that we save a lot of resources and time looking at the structure and get, like, let's say, educated guesses. Okay, so if this is the structure, what would be the best way of maybe blocking it or doing something different, right?
Not to drag this point a lot, there are mutations in non-charged amino acids that have tremendous, and I've seen in other contexts, they have tremendous consequences on the shape of the protein. And it could be where things are bending, or I don't think nobody knows. So then that ruins, like, and the number of experiments and simulations needed.
That would be nice.
Of course, there's no end to understanding stuff, and these ion channels are so fundamental that we cannot say we understand excitability in the nervous system until we really understand the ion channels, regardless of the practical uses of them, how soon we'll have them, or what they'll be. So thank you for coming to explain it to us, Carlos.
Yeah, no, I appreciate. Thank you. I really enjoy it. Thank you so much. Yeah,
it's great you'll join us. I hope you see you again on Neuroscientists Talk.
Yeah, absolutely. Yeah, glad.
Thanks, Fidel.
Thank you, Charlie.
Yeah.
This was really good.
Thanks, Fidel. Yeah.
This has been Neuroscientists Talk Shop.